Hey folks, I want to explain why you should even care about permutation groups. Why am I teaching you how to multiply things? Why am I teaching you how to put things in cycle notation? The answer I think is quite good. The answer is since any finite group can be written as a permutation group. So any finite group, any group with a finite number of elements has the same structure as some permutation group. So it allows you to give consistent notation for any finite group. Let me give you some examples of that. Let's look at the symmetries of the square in 3D. So I have 4 rotations, 1, 2, 3, and I guess I should have started with the 0 rotation, do nothing. And then I also have 4 flips, 1, 2, and then 3, 4. Important message here, you are awesome. I'm going to think of this as a permutation group, and we're going to permute the corners of the square. All right. So in my picture, I'm gonna draw a square, and let me give names to the corners. So I have corner 1, 2, 3, and 4. Okay. The rotation by 0 degrees corresponds to the identity permutation that maps corner 1 to 1, 2 to 2, 3 to 3, and 4 to 4. The rotation by 90 degrees, that corresponds to the permutation. Well, what does it do? It sends 1 to 2. And where does it send 2? It sends 2 to 3. And where does it send 3? It sends 3 to 4. And where does it send 4? It sends 4 back to 1. Rotation by 180 degrees. That corresponds to the permutation that sends 1 to 3. And it sends 3 back to 1. And this is the permutation that sends 2 to 4. And it sends 4 back to 2. All right, let's keep going. The rotation by 270 degrees corresponds to the permutation. So now we're rotating like this. We're basically rotating by negative 90 degrees. So it sends 1 to 4. It sends 4 to 3. It sends 3 to 2. And it sends 2 to 1. Okay, let's look at the flips. The horizontal flip, maybe I'll say it's the flip around this horizontal line. That swapped 1 and 2. And this horizontal flip swaps 3 and 4. This vertical flip, that corresponds to the permutation that it swaps 1 and 4, and it swaps 2 and 3. Okay, this will be my first diagonal. My first diagonal flip fixes 1 and 3, but it just swaps 2 and 4. And finally, my very last symmetry, this last diagonal flip, it fixes 2 and 4, but it swaps 1 and 3. Okay. So you don't need to you don't need to keep playing with square pieces of paper if you don't want to. You can just work now with this notation in this permutation group. So I haven't written down all of the elements of S4. You know, what's a permutation that's missing? We're missing the permutation 1, 2. Okay, why don't I have this permutation 1, 2? Why can't I swap just 1 and 2 swapping the others. Well, I don't want to destroy my card, so I'm going to use a piece of paper. Why can't I just swap 1 and 2? Well, if I swap 1 and 2 without swapping 3 and 4, I'm turning my square into this bow tie. Almost. Okay, so that's not a symmetry of the square, right? If I try to swap 1 and 2 while fixing 4 and 3, I'm not doing a rigid motion of the square. I'm totally destroying the square. Do you see that? So we didn't get the entire collection of all possible permutations on these 4 corners, okay? But nevertheless, we still modeled the group in this way. Let's do a problem related to this. So what do I get? Let's say if I do a vertical flip and then a rotation by 90 degrees. Okay. The way I'm going to think about this is I'm just going to multiply the corresponding cycles. So the cycle corresponding to the vertical flip is 1, 4, 2, 3. And then the cycle corresponding to the rotation by 90 degrees is 1, 2, 3, 4. Okay, so I can multiply these in cycle notation. Okay, and what does this give me? Well, I don't move 1. Let's start to see where 1 goes. I don't move 1, then 1 gets mapped to 4, and then 4 gets mapped back to 1. So 1 stays fixed, I think. Where does 2 go? 2 goes to 3, which doesn't get moved, and then it goes to 4. So 2 goes to 4. Where does 4 go? 4 gets mapped back to 1, and then that gets mapped to 2. So 4 gets mapped back to 2, so I'll close this off. And finally, I should ask where 3 goes. And 3 should get mapped to itself. And indeed, 3 gets mapped to 2, which then goes to 3. And another name for this is just 2, 4. But now I can look up, 2, 4 corresponds to this diagonal flip. So this tells me it should be this diagonal flip. Okay, let's check. Did the cycle notation algebra work? Or have I been pulling your leg? So let's do this vertical flip and then rotate by 90 degrees. And I end up like that. Okay, so the barcode on the bottom right, when I do this vertical flip and then rotate by 90 degrees, the barcode's on the bottom right. And indeed, when I do this diagonal flip, the barcode ends up on the bottom right. So I don't know if it's magic or just group theory, but yeah. So I think hopefully I've made the point that we've modeled this group, which is a pretty group, as a group of permutations. Furthermore, any finite group can be modeled as a group of permutations. So that's the importance of learning how to multiply permutations. Any group can be put in this consistent language. So, if you meet a new group and you're not sure which group this is, you could ask that group, how do you express yourself as a group of permutations, and try to relate this group to things you've seen before. Public questions? Thanks so much.